All right. So let's make sure we're recording here. Okay. So I am going to do the T2L3 notes. And y'all, some of this I'm going to jump fairly quickly to a calculator because we would use a calculator later on in the problem. Therefore, obviously, it would be calculator active. And I just do a lot of work that's not necessary if it is calculator active. So at least on a couple of these, that's what I will do. Now, the first part of this is going to seem a little bit overwhelming and not super duper calculusy. We don't actually do calculus until we get to the derivative and things of that nature. And you do see some of these problems in other maths, just solved maybe different ways. And then after we get through the first 5 examples, we're going to go into differentials, which is something you're way more familiar with. So let's just go ahead and get started. All right, so optimization and differentials. So we have the acronym up here. Nerds have equations for everything solved. So we look at what we need, what needs to be maximized or minimized, and that's going to be within the problem. It'll tell us that. What do we have? Do we have pictures, variables, quantities that don't matter? What equations are we going to use? And for equation number, for the second part of the equations, if the primary equation has more than one variable, write a second equation to relate the variables and use it to rewrite the first equation. So ultimately, again, you're going to end up with like 3 variables and we only want 2. So we're going to solve for one of those variables in a different equation and plug that in. And then we're going to solve by taking the derivative and verifying the results with sign analysis. Now, we won't actually verify our results with sign analysis, but like there's a couple of times the negative doesn't make sense and things of that nature. All right. A manufacturer wants to design a closed cylindrical container with a surface area of 75.4 square inches, including the top and bottom of the container. What dimensions will produce the container's maximum volume? So we're maximizing here. All right, so let's talk about, we have the surface area, and that formula we're going to use there. The surface area of the top and bottom is just going to be pi r squared. There's 2 of those, so 2 pi r squared. And then add the height in there, so that's pi r, 2 pi r h. Okay, so that's the surface area in general for a cylindrical container. All right, they gave us the surface area, so I'm going to go ahead and plug that in. All right, and then again, we're going to see that I have R and H here, okay? So I'm going to go over here and talk about what dimension will produce the container with the maximum volume. Well, we know that volume is going to be pi r squared h. Okay, we don't know the maximum volume. We don't know what dimensions. So there's all 3 things over here that we're missing. All right, so we're going to replace one of these with, I'm going to solve this equation over here for h. And the reason I chose h, you could have chose r. The reason I chose h is I only have one h. So that makes it way easier to get that by itself. Okay, so if I solve this equation for h, literally I'm going to move 75.4 minus 2 pi r squared divided by 2 pi r, and that would equal h. So now that can go over here into my h. Okay, and if we simplify this down, and I'm going to do that relatively quickly, okay, but if you simplify this down, you're going to see that the pi's will cancel, one of these r's will cancel. Okay, so now I've got r times all this divided by 2. So I'm going to go ahead and get 37.7 r. So that's this divided by 2 times that r minus, the 2's will cancel here, pi r cubed. So r went to both of these, 2 went into both of these, That's got me here. So now that's way easier to take the derivative of. Okay, so all right, dv/dr is going to be, and we're taking it with respect of r, so 37.7 minus 3 pi r squared. And we want to know, obviously, where that's going to equal 0. Solve that out. And I'm going to go out several decimal places here, further than what we normally do. But that's only because I want to have a value there. And you're going to see it wouldn't matter, because even if we rounded to 4, it would still just give us an r is approximately 2 inches. So we know what our r is. So then we're going to take that r and we're going to plug it back in over here to find our h. And that's going to give me 4.0001 is equal to h, or h is approximately 4 inches. So that's what we're looking for there. All right, for example number 2, which points on the graph y equals x squared minus 6 are closest to the point 0.05? Okay, so what you're trying to do here is you're trying to figure out, if I look over here at the point 0.05, 1, 2, 3, 4, 5. Okay, you're trying to drop a perpendicular. Obviously, I can't be exactly perpendicular. We want to go as perpendicular as we can to find the shortest distance there. And you're looking for these 2 points. Okay, so obviously what we're going to use here, if we're trying to find the length of that segment, is going to be our distance formula. Okay, so we'll make that ordered pair xy, because we don't know its values at all. Okay, so if we were to put that in from this point right here to here, okay, that would be the square root of x minus 0 squared plus y minus 5 squared. Okay, they told us what y is. This is y, so I'm going to substitute that right in here. So that would just be x squared plus 1/2 x squared minus 3. I just simplified that. Minus 5 quantity squared. All right, so if we clean that up just a little bit more, it's going to give us x squared plus minus 3 minus 5 is going to be minus 8. So 1/2 x squared minus 8 quantity squared. All right, and if you work that out, that would be x squared, and we're going to FOIL this out. This right here, we're going to FOIL this out. So 1/2 x squared times 1/2 x squared is going to be 1/4 x to the 4th. Okay, and then we would have 1/2 times negative 8, so that's going to be negative 4x squared, and there's 2 of those, so that's going to be negative 8x squared. And then negative 8 times negative 8 is positive 64. Okay, if you combine these, that's going to be 1/4 x to the 4th minus 7x squared plus 64. And I'm just going to go ahead and raise all that to the 1/2 power, just because taking the derivative is way easier once we have that 1/2 up there. Okay, all right, so now we're going to take the derivative of that. So that becomes negative 1/2 times, and that will be x cubed minus 14x. All right. So now if we go from there with that, you're looking for d prime. So the top would just be the x cubed minus 14x. And the bottom would be the 2 and all of this. Now, it looks like a lot right now. However, you're looking for where this is equal to 0. Well, we know that this function is only equal to 0 where our top is equal to 0. So that's all I have to worry about. So that gives me 0 and plus or minus the square root of 14. So I've got my x values. 0 doesn't matter. So our x values are going to be the positive square root of 14 and the negative square root of 14. And now I need to find my y's. They gave me y up here. So I'm just going to plug in for that. So y is going to equal plus or minus the square root of 14 quantity squared minus 6 over 2. So square root of 14 squared, whether it's positive or negative, is going to become 14. 14 minus 6 is 8. 8 divided by 2 is 4. So our two ordered pairs here are square root of 14, 4, and negative square root of 14, 4. So that's what you're looking for in that problem. Okay. All right, let's look at the next page. Okay, a rectangular page is to contain 32 square inches of print. The margins at the top and bottom of the page are to be 1 inch, and the margins at the left and right are to be ½ an inch. Okay, so what we've got is we have got a page in general. Okay, we'll make this X and this Y. And then outside of that, we've got margins around it. Okay, and it says the margins at the top and bottom are to be 1 inch. And on the left and right are to be ½ of an inch. What should the dimensions of the page be so that the least amount, so we are minimizing here, least amount of paper used, minimizing. And we're minimizing the area. All right, so if this was X, if I add ½ an inch on each side, then this is going to be X plus 1. If this is Y and I add an inch on each side, then this is going to be Y plus 2. So we know our area is X plus 1 and Y plus 2. All right, well, let's talk about, we've still got 3 unknowns, so I'm going to replace one of them. Okay, we already know that the area of the page itself is 32 square inches, so we know X times Y equals 32. You could solve for either one here. I am always usually just a habit of taking out the Y and replacing it with X. So I did that here, so Y equals 32 over X, so that's going to go in right here. And then we're just going to distribute this out. So if I do X times 32 over X, the X's cancel and I get 32. X times 2 would give me 2X plus 32 over X plus 2. So 32 and 2 gives me 34. And then that's going to be 2x plus 32x to the negative 1. Now it's just easier to take the derivative from here. Okay. So that goes away. We get 2 minus 32x to the negative 2. And we want to know where that is equal to 0. So where does 2 equal 32 over x squared? Cross multiply, 2x squared equals 32. So therefore, x squared is 16 and x is plus or minus 4. Obviously, x, we're dealing with a length, so we are going to throw out the negative here, and we're only going to deal with it being 4. So now once I know what x is, plug that in. So x plus 1 would equal 4 plus 1, which is 5. Then remember, y equals 32 over x, which is 32 over 4, which is 8. So then y plus 2 would equal 8 plus 2, which is 10. So the page should be 5 inches by 10 inches. Okay. Again, found X right here. Then I found Y, but the page itself was Y, or the outside was Y plus 2. So after I found the Y was 8, I had to add the 2 to get the 10. Okay. All right. So example number 4. So this is one of the ones where I am going to go down. I'm going to go to the calculator earlier than the work in Canvas is going to show. Just obviously one reason for time. But if we're going to use a calculator at the end, then it would be calculator from the beginning. Therefore, there's no reason to do as much as I do by hand necessarily. Okay, there is still several or a large part of it has to be done to get to that point. Okay, 2 posts, one 18 feet. Got an 18-footer. And the other is 32 feet. Stand 35 feet apart. So over here, 35 feet away is a 32-foot post. So we know this is 35 feet. All right. They are to be stayed by 2 wires attached to a single stake running from the ground level to the top of each post. Okay, so somewhere in here there is a stake and there's a wire that runs to the top of each one of these. Where should the stake be placed to use the least amount of wire? Okay, so let's just talk about what we know in general. All right, we do know these make right angles with the ground. So now you're looking at a regular right triangle. Okay, so we know we're going to use Pythagorean theorem at some point. Let's just we don't have a lot of measurements here, so let's create what they would be in terms of variables. So if I make this side x, then this side over here would be 35 minus x. Okay, I know nothing about the wire. I do know that these two lengths are not going to be the same. Okay, so I'm just going to make this one y and this one z. All right, so I did all that to just start creating some equations that we can manipulate. All right, so if I look at the left triangle, if I do Pythagorean theorem here, it's going to be y squared equals x squared plus 18 squared. And that would give me that y equals plus or minus the square root of x squared plus 324. So I've solved for a y. Good, because ultimately y plus z is the length of our wire. Okay, so I've solved for a y in terms of x. Now let's look at the other triangle. So it would be z squared equals 35 minus x quantity squared plus 32 squared. All right, work all that math out, and we would get z squared equals x squared minus 70x plus 2249, or z equals plus or minus the square root of x squared minus 70x plus 2249. Now we have y and z in terms of x. We know that we're looking for the length of the wire. Well, the length of the wire is going to be y plus z. So that's going to be, we're obviously going to take the positive, x squared plus 324 plus x squared minus 70x plus 2249. All right, so here is where, and I'm going to show you 2 ways I did this. I've already typed this in Desmos on my calculator. Now, obviously, I don't have the regular calculator with me here at the house. So I did use Desmos for this. But if you go into Canvas and you look at the key for today's notes, you're going to see I literally wrote all this out. I raised these to the 1/2 power. I took the derivative by hand. I wrote that out in something way prettier, in a simpler form than the negative 1/2 powers. And then I put it in the calculator. Okay. But ultimately, remember, we want to know where the derivative equals 0. So I'm going to show you And I've done it both ways here. All right, so the top equation is literally just the derivative of, let me write that out real quick. Okay, so if I did write this, if I took the derivative here, okay, or actually before I took, if I just rewrote this, it would be x squared plus 324 to the 1/2 plus x squared minus 70x plus 2249 to the 1/2. So that's if I got rid of those radicals. And you're going to see that's going to be the bottom equation there. Okay, so the top equation is where I went ahead and took the derivative. So in other words, I pulled the 1/2 down. I made that to the negative 1/2 power. I did the chain rule. So we're multiplying times 2x. Pulled this down, make that a negative 1/2 power. That gives me 2x minus 70. So all of that work, okay, again, you could have literally gotten to here and typed that in using Desmos, okay? So let me show you that. So the top, turn the top off, the bottom. We'll do this one first. Okay, so this is just what I had on my paper. The x squared plus 324 to the 1/2 plus x squared minus 70x plus 2249 also to the 1/2 if you go down here and look. Okay, and then I literally just took the derivative of all of that. And we want to know where the derivative equals 0. So that does cross right here at 12.6. Okay, so that's if I literally stopped at the square roots, put that straight in the calculator. If I got the derivative, I obviously wouldn't need the ddx if I've already done the derivative. Still, you're going to see it's 12.6. So either way you do this, you're going to get that answer. So again, if you go into Canvas and look at the notes for today, the key that's posted, it has all the work here. But ultimately, we're setting this equal to 0 when you do the derivative of that. Okay, and we all want all that equal to 0, so x is going to equal 12.6. So we know the stake should be 12.6 feet, and that's x, right? From the 18-foot post. And the reason I know that is because we made x up here our value from the 18-foot post. If you want to find how far it is from the 32-foot post, you would have to do 35 minus that to get that value. Okay. All right. So again, go back into Canvas. You will see those notes, the work for all of that by hand. Either way, you would have to jump to the calculator to get that value. So that's why I jumped just a little bit sooner. Okay. Example number 5, the demand function for a product is modeled by P equals 23e to the negative 1234014x, where P is the price per unit in dollars and X is the number of units. What price will yield a maximum revenue? Okay, well, we know revenue is going to equal P times X. So price times the number of units, okay, gives you your amount. So that's going to be 23e to the negative 0.123414x times x. Okay, and I just wrote that as 23x times e to the negative 0.00014x. All right, let's go ahead and take the derivative of this with respect to x. Okay, so the derivative of, we're going to have to do the derivative of the first times the second. All right, plus the derivative of the second. Chain rule that. Times the first. Okay, so I'm going to notice that if I was to look at these, this right here, both of these contain a 23e to our exponent there, so I'm going to factor that out. Okay, that will leave me with a 1. Now, I would say plus, but there's a negative here, so it's going to be 1 minus. I pulled this out and the 23 out, so that's going to be that shouldn't be there, sorry. 0.1231414x. All right, so now we want to set this equal to 0. Well, I know that there's nowhere that this right here is going to equal 0. So then I only have to worry about this. So 1 is going to equal this long number, and then that's going to give me $71,428.5714 is our X. So then to find our maximum revenue, the price that will yield the maximum revenue, we're looking for P. So P is going to equal 23E to the negative 0.1231414. And then you would take this whole value and put it in for X. And that's going to give us 8.4612. We're dealing with price, so we are going to round properly here, $8.46. All right, so now we're going to jump to differentials, which again is something that y'all are way more familiar with. Okay, let y equals f of x represent a function that is differentiable on an open interval containing x. The differential of x, denoted dx, is any non-zero real number. The differential of y is our dy. So in this situation, f prime of x is dy dx. dy equals f prime of x dx is what we've talked about. And then if you solve for f prime, it's just dy over dx. Okay. All right, so let's dive into these. All right, so the derivative of y, then we know, is just dy dx. And the derivative of the right side would be 12x cubed. So if we're solving for dy, just the differential dy, then dy would equal 12x cubed dx. All right, next problem. Derivative of y is going to be dy dx. And over here, we're going to have to do the product rule. So derivative of the first times the second plus derivative of the second times the first. And again, we're solving for dy. So dy is going to equal 10x plus x secant squared x dx. First part of these notes were way more in depth than the second part. All right. Letter C. Okay, take the derivative of y. We're going to go with dy dx. And then we do have to do the quotient rule here. So that's ho-de hi, hi-de ho. So ho-de hi minus hi-de ho over ho-ho. All right, so simplify this out. So it's going to be 2x squared plus 2x minus x squared over x plus 1 quantity squared. All right, so I'm going to simplify and solve. So I know dy is going to be over here. That's going to be 2x squared minus x squared is just going to be 1x squared plus 2x over x plus 1 quantity squared. and all of that has the dx at the end. All right, letter D. So dy dx. All right, so we've got derivative here is going to be secant tangent times inside will be 6x. And that's it. Sorry, that was crooked. All right, and letter E. So f of x is the same thing as y, so dy dx equals negative 2x cubed minus 7 to the negative 2 times inside will be 6x squared. So we know that's going to give us negative 6x squared on the top and 2x cubed minus 7 squared on the bottom. So then dy just equals negative 6x squared over 2x cubed minus 7 squared dx. Okay. And for the last one, there is a little formula that we're going to use here that I don't know why it's not on your notes. It should be on your notes. Okay, so let me write it in. Give me a second. There was a little supposed to be a little tidbit thing that showed up right here, but it's not there. Okay, let me write that in. All right, so differentials can be used to approximate function values. Using a function y equals f of x. We know that y and f of x are interchangeable, right? And the formula f of x plus delta x equals f of x plus f prime of x dx. Okay, and we're going to do this in this problem down here. I would not be super duper worried about this process, this formula. Again, it's just application that we're talking about here. Okay, so if we're going to use differentials to approximate the cube root of 8.7. So if I make f of x equal the cube root of x, all right, then f prime of x would be 1/3 x to the negative 2/3. Okay, so instead of cube root of 8.7, I'm going to make it cube root of x because we're trying to approximate here. Okay, so now if I use our formula, x plus delta x, that would be the cube root of x plus 1/3 cube root of x squared dx. Now, we're going to let x equal 8. And delta x is going to equal 0.7. So it's going to be f of 8 plus 0.7, which is what we have under our radical here. All right, so that's going to give me 1/12. 8 squared is 64. Cube of that is 4. 4 times 3 is 12 times 0.7. And that's ultimately going to give me 2.0583. Again, clearly that would be a calculator problem. Obviously, I wouldn't have to type all, or I wouldn't have to do all that math if it's a calculator problem. Again, don't get super frustrated or whatever on this problem in general. Okay. It's just an application of a problem. So f of x plus f prime of x dx, you're taking the derivative. Your dx is going to be the 0.07 because that's going to be the difference here. Again, just an application problem there. All right, so you do have homework T2L3 that you're supposed to be doing. We will jump into, I think I said I'm going to change our lesson plan. So go check Canvas for what we'll do tomorrow. Your quiz will be Wednesday. All right, so I will see you all tomorrow. Make sure you get these notes filled in. If you have any questions, make sure you bring them with you to class. All right, y'all stay safe, stay warm. See you tomorrow.